This is a metal tube. There is no rotor inside, no gearbox, no piston, and no hydraulic fluid. Yet, when heated, it can twist, produce torque, and pull a heavy mechanism into motion. In one NASA test, a nickel-titanium hafnium torque tube controlled an FA-18 wing section weighing about 300 pounds. It produced 5,000 inch-pounds of torque, roughly 565 Newton-meters, and moved the wing to selected positions within the tested range. But this tube is not a conventional motor. It creates no rotating magnetic field, and has no rotor converting electricity into continuous motion. The action begins inside the material's crystal structure. So how can heat turn a stationary tube into a rotary actuator? And if heating is enough, why has this metal muscle not replaced motors and hydraulics everywhere? A torsional SMA actuator still needs familiar hardware. A support housing, bearings, a load coupling, a heater, a heat rejection path, and position sensors. The difference is its force-producing element. Instead of a motor and gearbox, it uses a shape memory alloy tube, commonly from the nickel-titanium family, and sometimes modified with other elements to change transformation temperature or durability. One end of the torque tube is fixed. The other connects to an output shaft or hinge. A resistive element or another electrical arrangement heats the tube. As its temperature moves through the activation range, the output rotates. Reverse motion does not appear automatically when the power is switched off. Many designs need a torsion spring, a bias load, or a second SMA element acting in the opposite direction. After cooling, that return system restores the tube's initial deformed state. So claiming that the whole actuator has no moving parts would be inaccurate. The SMA force element has no internal sliding components, but the complete device still contains a shaft, bearings, couplings, and a return mechanism. Nor is the tube merely expanding like ordinary metal. Normal thermal expansion is too small, and does not generate a large twist by itself. The useful motion comes from a reversible solid-to-solid phase transformation. A shape memory alloy has two important structural states. At lower temperature it is martensite, in which crystal variants can reorient under load. At higher temperature it is austenite, associated with the shape previously established for the component. During manufacturing, the tube is formed, and heat treated to establish that shape. Once cooled into martensite, it can be twisted away from it within a recoverable deformation range. When heated, martensite transforms back into austenite. The material attempts to recover the established shape, and the tube untwists. With free output, recovery creates angular displacement. When a load resists it, recovery creates torque. Heat has become mechanical work. But the material does not switch at one exact temperature. During heating, austenite starts forming at one threshold and finishes at a higher one. During cooling, martensite returns across a lower range. The separation between these paths is thermal hysteresis. That produces a control problem. The same temperature can represent two different material states depending on whether the actuator is heating or cooling. Switching off the current also does not produce an immediate return. Stored heat must escape, while geometry, load, and airflow affect the cooling rate. How can engineers turn a material with hysteresis, temperature-dependent response, and limited angular travel into a compact, powerful, controllable rotary mechanism? The answer is to design the material and mechanism as one system. First, the torque tube must be trained. The metal is not thinking or storing an image. Training means heat treatment and thermomechanical cycling that stabilize a repeatable response around a designed shape and temperature range. In the cool state, the return mechanism twists the martensitic tube away from its remembered position. The controller then powers the heater. As heat enters the tube wall, the austenite fraction rises and recovery stress develops. Once SMA torque overcomes the opposing load, the output shaft rotates. A position sensor tracks the angle so heating can be reduced or stopped at the command. To reverse, the system must remove heat. As martensite forms again, the spring or opposing element can reorient it more easily. That return load twists the tube into the state required for the next cycle. A longer tube can create a larger twist, but occupies more space. NASA developed multiple concentric SMA tubes connected so each element's angular deflection accumulates at the output. For the same required angle, the actuator can be shorter. For the same length, the nested arrangement can increase angular displacement and output capability. This remains limited travel rotation. Continuous rotation requires another transmission architecture. In a separate ring drive design, several SMA tubes perform short torsional strokes in sequence. Locking and transmission mechanisms deliver each stroke to a ring gear while other elements reset. Coordinating those cycles lets the output continue in the selected direction rather than twisting forward and returning. The actuator therefore does not eliminate mechanics. It replaces the conventional force source with an active material, then uses mechanical design, thermal management, and control to harness the phase transformation. Now place the cycle inside an adaptive wing. The flight computer commands a wing angle. The controller energizes the heater around the torque tube. Heat enters the wall and drives the martensitic to austenite transformation. The tube tries to recover its established shape, applying torque to the output shaft. The shaft moves the hinge while a sensor compares actual and commanded angles. Near the target, the system adjusts heat input to prevent overshoot. To reverse direction, it reduces heating and increases heat rejection, or activates an opposing element. As austenite transforms back into martensite, the return load recreates the initial twist. The actuator is ready for another command. NASA demonstrated this idea at two different scales. On the small uncrewed aircraft used by the Spanwise Adaptive Wing project, an SMA mechanism folded the outboard wing from horizontal to 70 degrees upward or downward in flight. In a separate ground test with a full-scale FA-18 wing section, a nickel-titanium hafnium torque tube controlled a structure weighing about 300 pounds. These tests show the appeal: a compact force element with high power density, and no pressurized hydraulic fluid system. They also expose the limits. Speed depends on adding and removing heat. Hysteresis makes temperature to position behavior non-linear. Excessive stress or poorly controlled transformation can accumulate deformation and reduce stability over repeated cycles. SMA service life is therefore not one fixed number. It depends on alloy composition, strain, load, maximum temperature, heating and cooling rates, and training data. A mechanism designed for slow and frequent motion may be an excellent fit. One required to reverse dozens of times per second presents a very different problem. An SMA tube produces torque, not because the metal is alive, and not through ordinary thermal expansion. A shape is established in the material, torsional deformation is introduced in martensite, and transformation back to austenite forces recovery during heating. Place that recovery under load and it becomes torque. Add heating, cooling, a return mechanism, sensors and control, and the tube becomes a complete rotary actuator without an electric motor, piston, or hydraulic system as its primary force source. But heat is also the limit. Phase transformation gives the actuator its strength while constraining its speed, accuracy, and service life. Shape memory alloys do not replace every drive system. They create a different class of machine, in which the material does not merely carry the load. It becomes the component that produces motion.